Hello there. In this video, let's use conservation of energy to derive the classical expression of escape velocity. And then what we're going to see is that this convenient form of escape velocity can actually be used rather conveniently to come up with the expression of what's called a Schwarzschild radius of a black hole. And then we can talk a little bit about event horizons and a specific example of Cygnus X-1, which is pretty interesting. Alright, but let's go ahead and start by applying conservation of energy here. So here I have this situation where I have a planet of mass capital M, and I have some little body on the surface of the planet of mass little m. Right, in this condition here that the mass of our planet is significantly bigger than the mass of our body is what allows us to treat our planet as though it's stationary. Even though in our mind, if we imagine that this arbitrary body here is some distance away from our planet, the force of gravity between these two objects is mutual with each other. So we could imagine that this planet here is moving very, very slightly. But because the mass of the planet is just so much larger than our body, we assume this motion of the planet to be completely negligible. Okay? And so effectively we can always treat the planet as though it is stationary, and only this mass little m is moving with respect to the planet. So the first thing that we need to do is we need to define the notion of escaping, right? And so what that means for this mass little m here to escape this planet of capital M, that means that the mass little m has to move so far away from this planet. It has to move so far away that it can really no longer feel the gravitational pull from the planet. Okay, so our mass has to move so far away that it can practically no longer feel the gravitational pull from our planet, right? Now, how far away is that? It turns out it's infinitely far away, right? Let me go ahead and call the distance from our surface of our planet. I'm going to go ahead and call this distance little r, right? Then the gravitational force, I'm going to call this F sub g, right? The magnitude of this force, F sub g, we could write out as capital G, capital M, little m, over little r, plus, remember, capital R, we have to take the distance between our body and the planet's center of mass, so we need to add in a little r just like that, right? And this whole thing gets squared. This is Newton's inverse square law for gravity. Now, this gravitational force, it's never going to go to zero for finite values of little r. This is always going to give us some value. However, if we take the limit as r goes to infinity, right, then we basically have a denominator here that's going to be infinity, and any finite value divided by infinity, right, you can imagine that in your mind, that's going to limit towards zero. Okay, make sure that you understand that concept, that if I take this constant value, some finite value, and I divide by a really, really big number, an infinitely large value, that is going to give me zero, right? So we have to imagine this situation where my little body here moves infinitely far away from my planet to truly escape its influence. Alright, so now that we have the notion of this escape distance that we need to get to, let's define the notion of escape velocity. Let's imagine that we were launching this little mass, little m here, out of a cannon, right? And we launched it such that we could provide it with some v. And if this cannon shoots our body fast enough, with this minimum escape velocity, then it'll shoot it so fast that the mass is able to actually get all the way out to this infinitely far away distance without getting turned around by the Earth's gravitational force. So as long as we provide a velocity equal to or larger than this escape velocity, our body here, it's going to get shot out, and it's just going to keep moving and moving further and further away from the planet. It's never going to get pulled back or turned around, right? And so to derive this escape velocity, we can really nicely use the conservation of energy. Why do we get to use conservation of energy, by the way? Well, our body here, right, we treat it as an idealized rigid body, which means, it only has just the 1 degree of freedom. We can effectively treat this guy like a single particle, okay? And when you have a single particle, all that we need to do is we just need to check that the forces on our body are conservative, right? We just need to check that the forces on our particle here are conservative. After we've checked that, we have nothing but conservative forces on our particle, then check, we can use the conservation of energy, right? And in this case, we only have one force. We have the force due to gravity, which is a conservative force, and so check, because I have nothing but conservative forces acting on my little particle here, then there we go. We can use conservation of energy. So, using conservation of energy, I know that the change in my particle's potential energy plus the change in its kinetic energy is going to be equal to 0. Okay, now these deltas, we can always imagine writing them as, in this case, this potential energy, we could write out as our final potential energy minus our initial potential energy, and we can do the same thing for this kinetic energy here, plus our final kinetic energy minus our initial kinetic energy, and this all equals 0. Right, so now we just need to figure out what these terms are. Let me give us a little reminder here, okay? Let me give us a little reminder that our gravitational potential energy function is defined as minus g capital M little m over r. Okay, zooming out here, okay? Right, so if I'm just on the surface of this planet here, then that means I am a distance of capital R away from the center of my planet. So I just plug in capital R for this potential energy expression here. So I have minus g capital M little m over r, just like that. And my initial kinetic energy here, well, right now my mass has this escape velocity with it, and we know that kinetic energy is 1/2 times little m times, in this case, v escape. We plug in v escape for velocity squared. That's the expression for kinetic energy, okay? And if my mass here ends up traveling infinitely far away from the planet, we take this limit as r goes to infinity, okay? Then what's the final potential energy going to be? The final potential energy, this guy here, is going to go to 0, right? Because we have minus g capital M little m over capital R plus little r, but this little r goes to infinity, just like what we showed with the force here, okay? So our final potential energy is going to end up being 0. What about our final kinetic energy? What about our final kinetic energy here? Well, for the minimum escape velocity, right, this guy is going to go to 0 also. My particle has been given just enough initial kinetic energy such that when it gets infinitely far away from the planet, it's stopped. Could we give it more kinetic energy? Absolutely. If we gave it more kinetic energy at the beginning, it would keep moving out. It would get infinitely far away, and it would still have more kinetic energy. So we can always give more kinetic energy here at the beginning, such that when my body gets infinitely far away from the planet, it still has some spare energy left over. That's okay, but for the minimal condition to provide this escape velocity, we've given just enough initial energy to the particle such that it doesn't have any kinetic energy left over by the time it's escaped the planet. And so if we're feeling great about that, let's just pay attention to our signs here. I have a minus and a minus here. Minus, minus, this is going to be positive. So I have g capital M little m over r. And I have just this minus sign here. Minus 1/2 m v escape squared equals 0. Let's solve for our escape velocity. The masses little m are going to cancel out, and we can rearrange this almost immediately. We have v escape is equal to the square root of 2gm over r, right? Just a tiny little bit of algebra and we get this guy here. Now, it turns out that if we define our escape velocity, v escape, if we define this to be the speed of light, c, right? If we define our escape velocity to be c, then this expression becomes very interesting. Let me go ahead and solve for r with this, and then we'll discuss the results. So I'll square both sides. So I'll have c squared equals 2gm over r, or r is equal to 2gm over c squared. Now, I'm going to put a little subscript s on this r. This r sub s here is defined as the Schwarzschild Radius. Right, and so this Schwarzschild Radius is a very important parameter in describing black holes. If I have a black hole, and this black hole, what general relativity really predicts is that this black hole is a singularity. It's a point of like infinite mass here, okay? Because the gravitational forces at play are so strong that everything collapses in on itself. Okay, so that's predicted by general relativity. But now, this Schwarzschild Radius that we've come up with, this guy here, okay, what we're saying is we have some radius, right? We have some radius r sub s that defines this sphere around this black hole. And if I'm on the surface of that sphere, okay, if I travel with the speed of light c, that is just enough velocity to be able to escape this black hole. But if I go inside, if I go within the Schwarzschild Radius, even if I'm traveling with the speed of light c, I'm not going to be able to escape the black hole anymore. I'm going to get pulled into the singularity. Now, the way that we came up with this expression for the Schwarzschild Radius, by, plugging c in for our escape velocity, total hogwash, okay? Because the real way that we got to escape velocity was to assume this classical expression here for our kinetic energy. And so what we're really claiming by just quote unquote plugging c in here is that, the expression for kinetic energy of a photon is like 1/2 mc squared, which is just nonsense, right? You have to, if you want to talk about light in any meaningful capacity, we have to use relativistic physics. But it turns out we just get really lucky by doing this kind of archaic substitution of c in for v escape, right? If you ended up going through the general relativistic route, you'd end up getting the exact same expression for the Schwarzschild Radius, which is really neat. But I think it's a really cool way to kind of intuitively connect in escape velocity, because we can immediately see the exact physical significance of this Schwarzschild Radius, because we all know that nothing in the universe can travel faster than the speed of light. That's a law defined by relativistic physics. So if you're within the Schwarzschild Radius, you're in the no-go zone at this point. You're done. So it's a really nice kind of easy parameter to define black holes with. Okay, and so this shell, or this boundary here, this boundary at which once you go past this boundary, there's no return possible. It's your point of no return. You call that your event horizon. Okay, so that of course is intimately connected with your Schwarzschild Radius. So this boundary is your event horizon. So let's go ahead and quickly apply this formula by looking at an example with Cygnus X-1. So in the 70s, it was discovered that in this Cygnus constellation here, Cygnus is Latin for swan, right? We can see this constellation kind of looks like a swan with its wings extended out, right? There was discovered a black hole, which was labeled Cygnus X-1, okay? And the mass of that Cygnus X-1 black hole was determined to be 21 times the mass of our sun, or, approximately 4 times 10 to the 31st kilograms. Okay, these are some rough numbers. Now, if we wanted to find the Schwarzschild radius of Cygnus X-1, well, let's go ahead and just plug right into our formula. Remember, we have Rs equals 2gm over c squared. We're going to plug straight into here. So plugging straight into here, we have, this is going to be 2 times 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared times our mass, right? 4 times 10 to the 31st kilograms over, what's the speed of light? That is 3 times 10 to the 8th meters per second, and we square that. right? And plugging in these values in, we'll find that the Schwarzschild radius is going to be approximately equal to 60 kilometers, right? This is our Schwarzschild radius for Cygnus X-1, right? And so we can see that this is really small, right? If I write down the radius of the Earth, this is on the scale of 6,000 kilometers, right? So what we can really see is that the Schwarzschild radius of Cygnus X-1 is really just like 1% of the radius of the Earth. And yet Cygnus X-1 has the mass of 21 suns. So you can really start to get a sense of the scale of these black holes, right? Right, the effective density here is no joke, and there's plenty of other ways that you can compare these numbers to get a sense of scale. But anyways, I'm probably going to go ahead and end the video here. Actually, really quickly before I end the video, let me also just go ahead and note, because this is fun, the event horizon radius of Cygnus X-1. Okay, so experimentally, right, this is really discovered to be around 44 kilometers. Right? So what's our difference between our experimental result and this calculated result? Of course, there was some rounding done in this calculation, but a little bit more fundamentally, right? There's limitations in our model of this Schwarzschild model for a black hole, right? We're not accounting for example, black holes can have angular momentum associated with them and also charge. So these kinds of nuances, you can only explore by actually looking at, general relativity and in essence, improving our model from the Schwarzschild black hole to, for example, a Kerr black hole, which captures this angular momentum, right? But anyways, even this Schwarzschild model, we can see, gets us the right idea, and we can continue to improve our models from there. But anyways, if you enjoyed this video, found it interesting, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.